In the last video, we took a look at angular acceleration, and now we're going to go and look at how we can cause angular accelerations. And this is also due to forces, but we need to define a quantity that describes how forces make things twist. So the quantity is called the torque. If you have friends who are in engineering, they'll often call it a moment, which is short for moment of force, but that can be confused with moment of inertia, which sounds very similar because it also often just gets called a moment. And so the physics community has gravitated around using the term torque. So let's think about how you can make a door twist about its hinge. Certainly you can make it twist about its hinge more readily if you push harder on the door. But there are other things you can do to either help or hinder your case. For instance, it'll be easier to push open a door if you push on the side of the door away from the hinge. It'll be harder to open the door if you push on the side of the door closer to the hinge for the same amount of force. And maybe even a little less obviously, but it also matters. It matters which way you push. If you push directly square onto the door, it'll open up easier. But if you push more parallel to the surface of the door for the same amount of force, it'll be harder to open. Probably may not have thought about that too much using your hands, but if you've ever had to, like, say, try to force a door open with your foot because your hands are full, you may have run across that. So it appears to matter how hard you push, where you push, and which way you push. So we need to encode all of those into it. And it turns out that our definition of torque will do all that. So we will start by defining an axis of rotation. So this axis of rotation is pointing in and out of the screen at you. I just drew an X showing where it cuts through the screen, but it's actually a line that goes in and out of the screen. Now over here, at this point right here, we'll call this the point of application of the force. So this is taking care of the where, because the where it matters is in relation to the axis. So we have our axis and we have labeled where we're applying the force. So we'll go ahead and let's just say we exert the force this way. Now you can see here, it's going to try to cause this object to go around this axis. And a physicist has to take a very generous view of this. If an object is going in a straight line even, that can be seen as going around some axis just very badly. So even things that aren't moving in circles, we can still talk about the torque about some axis. And I should also point out that this axis of rotation is completely arbitrary. You can pick any axis of rotation you like to analyze how forces are attempting to twist things around that object. But usually there's a natural choice, like a hinge or a axle or something like that. So we have to figure out how to encode the which direction part, and there's a couple different ways to do that, and I'll get into them in turn. The standard thing you do is you extend a line that goes through the point of application lined up with the force. This line gets called the line of action of the force. So conventionally, we'll be putting our coordinate system at the axis. So this would be the position of the point of application. But it'll turn out, if you think about it carefully, remember we said that you'll get the most bang for your buck trying to open a door if you push square or perpendicular to the door itself. So what's going to matter here is this distance perpendicular to the axis. So this usually gets just labeled R perpendicular, but it has a couple of different names, and I'll probably use them about 50-50. It'll either get known as the lever arm, or it's also known as the moment arm. So with all of that, we can now define the torque to be the product of the lever arm and the force. So this funny letter here, this is another Greek letter. It is a lowercase Greek tau. So if we go back to the special paper we all learned to draw with, there are two ways that people draw taus. They either draw it like this or they draw it like that. Either way, there's usually a little hooky at the bottom like that. Okay. Now, if we go and take a look at this for a moment here, we realize that if we can figure out our perpendicular here, if we say that this angle here is phi, if I move the position vector so that it shares a common tail with the force vector like so. So here's my angle phi. So there's the force, there's the position vector. I can go and project out here. I can go like this, and this angle here would also be phi. And this piece here is our perpendicular. So this is the opposite of phi. So we could also write this as RF sine phi. All right, now let's take care of sines here. So a torque will be assigned a positive value if it's attempting to twist something counterclockwise. So what I drew here, we're going counterclockwise-ish. And negative if the force is attempting to twist something clockwise. Of course, you're free to define otherwise, but if you do, you need to say that out loud. This is the default choice. So the units of torque are Newton meters. Now, looking ahead a little bit when we get to energy, I'm just going to put in right now that this is not a joule. If you don't know what energy is yet, that's okay. I mention this because it turns out that because angle doesn't have a physical dimension, this torque and energy wind up actually both having the same physical dimension. So in order to tell them apart, we write the units differently. So in the SI system, we write the units of torque as Newton meters, and when we get to energy, we'll write them as joules. The upshot here is that here we are trying to describe the effect of a force being applied at a distance, and energy will be related to the work-energy theorem, where work is attempting to describe the effect of a force being applied through a distance. So the distinction between at and through is really crucial, but it doesn't show up in the units. So we write the units differently so that we can keep them straight. All right. Now, another way that we could write torque is we could say, well, wait, I don't have to multiply r by sine phi. I could have just as easily multiplied that by f, right? Because multiplication commutes. So how could we interpret that? Probably easiest to think about if you're like turning a wrench trying to break a bolt or something like that. So let me try to draw a bolt. Yeah. That's okay. My wrench is probably going to be worse. If you actually used a wrench that looked like this, it'd probably be a bad sign. All right, and I wound up drawing my wrench too close to my words, so I need to move my wrench. There we go. So again, here, you would probably be applying your force. Say here. Now here, I'm doing kind of a bad job of it. We all know that you should be pushing like this on your wrench, but let's say you don't have good reach where you're trying to twist a wrench. That always seems to be the case. So you might not have a choice in the angle that you are twisting with. All right, so this would be my R because the bolt would be my axis of rotation here. And so if we go ahead and work through the trig of it, and I'll leave it for you to do the geometry in the trig, but you should be able to convince yourself that the tangential component of the force here, so that part of the force that is tangent to the circle that we would get here, the tangential component of the force turns out to be equal to F sine phi. So another way we could write the torque, if we find it convenient here, would be to say that it's equal to the entire distance from the axis to the point of application times the tangential piece of the force. So this is the part that's actually trying to make something go around in a circle. This perpendicular bit here, this radial bit, is only serving to try to compress the wrench. It isn't trying to actually twist anything. Alrighty, so let's say you have more than one force being applied on something. These forces could be attempting to cause the object to twist in different directions. So again, I want to be abundantly clear here. Torques are due to forces. They're not a different physical quantity. It's only just trying to describe how a force is making something twist. So let's say you've got some oddly shaped thing like this. I'm imagining some sort of flat object. And let's say it's attached onto an axle right here. And let's say forces are being applied at 4 different spots here. Might be a force here, let's say. There'll be a force here. Let's say that there's a force here. And maybe for completeness sake, let's say there's a force there. So in general, these forces probably aren't going to cancel. The way I have this drawn, there's a pretty steep downward component. So the axle itself is going to have to push against the object. So first off, let's think about what torque that force from the axle applies. So let me just draw it over here. And when we talk about torques, we always draw in our torques, our forces at their point of application. This is leading towards something we'll call an extended free body diagram. So let me go ahead and draw the line of action here. So when I draw the line of action, what I see is that the lever arm is 0. So another way we can think about the lever arm, if it's helpful, is the lever arm can also be thought of as the shortest possible distance from the axis to the line of action, whatever that is. Here, the line of action goes right through the point of application. So the shortest possible distance from right through the axis. So the shortest possible distance between the axis and the line of action is, well, 0. So we can write that our perpendicular is 0. So then the torque due to the axle itself on the object is also 0. It's kind of a handy result to keep in your back pocket. So what we realize is that the axle itself doesn't attempt to cause things to twist. But then if you're just trying to describe the net influence of all of the torques due to these forces, you just add them up. So we will define the net torque to be the torque due to the first force plus the torque due to the second force plus the torque due to the third force plus the torque due to the fourth force plus and such. All right, so how do we handle gravity? Here I can't get into the tedious details of the derivation. They involve math beyond the scope of this presentation. So I'm just going to have to ask you to take it as a statement of fact. Let's say I've got another misshapen object here. Let's say this is my axle. If I'm trying to describe gravity, what you can do has been rigorously shown that if you calculate where the center of mass of the object is, you can pretend that the entire force of gravity is being applied at that center of mass. So here I'm imagining like a disc, a flat object here that's hung on axle vertically. So it'd be free to spin around the axle. So then the lever arm for gravity would be that distance right there. So even though some of the mass is to the left of the axle and is trying to twist it counterclockwise, and some of the mass is on the right of the axle here trying to twist it clockwise, the net result, there's no need to divide it up. The net result of it all has been shown to be just pretend the entire force of gravity is entirely being applied at the center of mass of the object. Alrighty, so in the next video we will get into Newton's second law for rotations. And I like to be a bit of a pedant here and say that's more correctly Newton's second law applied to rotations, but we'll get to that in the next one. Catch you there.